Topic is about understanding enough of queuing theory to be dangerous. Dangerous in a positive sense, where we are able to build systems that are better and and work well in a sync manner instead of shooting ourselves in the foot, kind of dangerous. So, as Shiva said, I'm Chinmay. I go by Chinmay 185 as the handle. 185 happens to be like the first random number that I 3-digit random number that I used uh, to get a unique username, so that I can use that same username across all of social and all media. That's the story behind 185. I'm a founder at 12n, where we focus on improving backend and site reliability engineering for various companies. We work with startups and scale-ups, mostly Series A or above companies. I write stories on some of the pragmatic software engineering that we do, both at 12n, and I've been trying to talk to people to hear their stories that I can read them more on Twitter and other social media. Personally, I love engineering in general. I like psychology, human psychology, uh, motivation, that kind of stuff. Like what motivates people. In general, a lot about human consumer psychology and general psychology concepts. I also love percussion. I play tabla. Tried drums, but yeah, didn't get time to get better at it. And I love a game called Age of Empires 2, to be precise. If people here have played that game, then it's a very old game, but super interesting strategy game, which combines a lot of strategy, both like short term and high level kind of strategy. Pretty interesting game. So that's about me. Uh, so today's agenda is going to be why we should study queuing theory, a brief idea about what it is, why it matters, etc. We'll talk about just enough of theory with ideally an example to make it easier for people to understand. As I said, I was just talking sometime before. I'm keeping this a bit light and not too much theory. If there's interest from many people, and if I actually get time to prepare a good detailed deep dive talk, I'll do that later. Mainly, I want to talk about like a couple of production use cases. There's one production use case that that I worked on a couple of years ago. There's also a recent one which happened to be very similar in terms of architecture. I want to talk about those two use cases and see what concepts of queuing theory we applied, how it was helpful to learn that essentially. So, and a bunch of references around what you want to do if you're interested in this stuff, what to do next. Yeah, that's the overall agenda. I usually like to start with some sort of a empowerment promise. Big word, I know. Where idea is, why should you attend this talk? So if you want to get better at building asynchronous systems, this is hopefully the talk where you'll get to see how async systems work at a high level. So my promise is to take you from person on the left to person on the right. It's very hard to do that in just like 15-45 minute talk, but we'll try to do our best to at least give you an introduction of various high level concepts so that you can go deep dive later. It is going to be theory coming from some practical angle with some applications of that theory to our production use cases, and not just deep dive theory, because again, from engineering point of view, we care about cost and benefit trade-offs of things. So I'll cover enough theory to look at and to apply that to practical purposes. So we'll not cover deep dive equations like what you see in this book or in the screenshot. By the way, this is from one of the interesting book by Robert Cooper. I went down this whole, read a few pages. A lot of it went above my head, and but we will not go deep dive as this book, but more like this, where we'll talk about what are very high level characteristics of any queue and how do we denote queues and what do we make sense of a queuing system. Don't go about reading all of that just now. I'll cover all of this going forward. Right. So start with basics, right? What is a queue? It's basically a line of people, jobs, or things waiting for their turn to be processed. It can be, we've seen queues in real world, airplanes waiting to land or take off, jobs or products on an assembly line to be processed, and some queues that we all hate, traffic, right? Nobody likes to be in traffic queues, but this is what life is about in general. Why we study queuing theory? It's like a mathematical study of why and how waiting lines work and how to make them better, right? The goal is to improve the quality of service. One of the reasons is in ideal world, we would like to eliminate all queues, but that is almost impossible given the practical nature of world. So there are going to be queues. We can study the queues to get better at having shorter waiting time for customers and having better kind of service model, right? That's the purpose of studying queuing theory in general. So let's take an example of a queue, typically, let's say at a supermarket, right? Where there's a server and there's a bunch of customers who are waiting for their checkout, right? So customers encounter what we could call it as waiting cost, where they have to wait for their turn to be processed. So they are in the queue and waiting for their turn. From the server or the cashier or even, let's say, owner of a supermarket, from their point of view, they are going to have service cost, right? It takes like a person, or there's automated systems right now these days, but it still takes a service cost to be able to serve a bunch of customers, right? So in order to remove waiting cost, we would have to add more service cost where we have more checkout lines, faster checkout and whatnot. Whereas if it's small enough store, it is going to increase your cost, right? So total cost for queuing, you could calculate it from a point of view of both, which is the waiting cost for the customers and the service cost. What we like to look for is some sort of equilibrium where if you look at this graph, on the x-axis we have capacity, which is this, what is the capacity that we can provide to be able to have lower waiting time for customers, right? So if you see the capacity as it increases on the x-axis, the waiting cost for customers is going to go down like this. And on the y-axis, we have costs, which is the service cost, right? Where as you increase capacity, that means you're incurring more and more, adding more and more service channels or personnel or machines, etc., which is going to increase your service cost. What we ideally want is some sort of optimal zone where customers don't wait that long. At the same time, the costs for service are not too high for us. Right? It's just kind of the equilibrium point. Here, this graph is very simplistic. It shows a point to be a literal point in 2D. Usually that is not the case. It is more like a spectrum or more like a blob where you play with some of these variables in terms of cost, capacity, and performance to be able to achieve what you want, right? And it's more like a triangular area between cost, capacity, and performance. That is what we're aiming for overall from studying queuing theory point of view. So let's take a look at some of the important concepts of the queuing theory. But again, extending our supermarket example. So let's say we have, we have this server and customers, and there's a source of customers who are coming into the supermarket, right? So using this, we can take a look at not just characteristics of queues at the supermarket, but in general, how queues form or what are the fundamental blocks of building a queue, right? If you think about it, it is in case of supermarket, it's how customers enter the queue, right? What is the rate at which they enter the queue, for example? What's the distribution? How they leave the queue? That means how they get serviced. Like if it takes them more time per customer to be serviced, then what is the distribution duration and stuff like that, right? So how people enter the queue, how they leave the queue. This all also depends on the number of people serving these customers. So in this case, in the previous example that you saw, there's a single server where there's a single queue where all customers wait for their turn, right? But you could add multiple people, and then hopefully the waiting time for customers would go down. Right? There is also something known as queue discipline, or the order in which customers are served. Right? Typically, this is first come, first served basis in case of supermarkets or typical queues, but there are a bunch of other alternatives that you could consider as well. Then comes, these are sort of extended sort of variables if you think about it. Like what's the maximum number of customers allowed in the whole system? If you think of the whole supermarket as a whole system, how many customers will be allowed in the system? This can be finite, infinite, things like that. And similarly, where is the source of customers, right? Is that also finite or infinite? It's almost like a source and a sink in some ways, right? So if you think about it, all queues have these characteristics. Take any queues in real world or in our software world, where if we say a server serving HTTP request, it is also some sort of a queue where there are requests coming into the server. There is some latency where the server is serving these requests, and then the response is sent back to the users. Right? The more number of servers you add, the better hopefully the service time will be. And how you handle these requests, do you have a load balancer, stuff like that. These are 6 characteristics which are common for all queues in general. So let's look at them in more detail. So typically, again, in case of supermarket, if we think about it, how customers enter the queue. Imagine here's a single server and customers are entering typically. Typical behavior that we've seen in practice is the inter-arrival time between customers or most processes would be Poisson distribution, right? I'll cover what Poisson distribution means and what negative exponential distribution for service time also means in the next slide. But idea is that people arrive at some sort of random Poisson distributed interval time, and they get serviced at certain intervals and they leave the queue, right? So typically, if you were to look at the difference between these or what these really mean, this is about counting how many times something happens in a certain amount of time. Whereas negative exponential distribution is more about the time you wait between each thing happening. This is still very abstract and might be confusing. So let's look at like some concrete examples, right? Imagine you are counting how many birds are sitting in a tree per hour. So you just sit down, you watch a tree and you count how many birds are actually landing on the tree for a long duration, and you average this out for the time that you watch the tree for, right? So this kind of distribution would be known as the Poisson distribution. In case of negative exponential, what we look for or what we are looking for is not how many times birds are landing, but what's the duration interval between each bird landing on the tree, right? So one bird lands, some time passes and the second bird lands. What's that time? And we're tracking the interval of time across a long length, right? And we look at that average or a mean value over a long period of time. Similarly, in case of supermarket, it would be counting how many customers end up in a checkout queue at the supermarket, right? The people who are joining the queue. How many end up joining the queue in a long enough duration of hours? I divide that by the number of hours and say, okay, on an average, we see 25 people join the queue in an hour, right? Overall, throughout the 24 hours of operation of the supermarket, for example. Similarly, if we look at the negative exponential distribution, it would look at some certain things like how long until the next customer from the supermarket checkout queue is served. So there's one customer already there. It takes 2 minutes on an average to serve that customer, and then the next one you try to serve them. Right? So what's that duration of time? Why this? This is where it gets a bit more sort of technical, where there is bunch of distributions for how customers or how jobs enter a queue in general, right? If you look at sort of what are various possible ways in which these distributions are defined, Typically, you'll have Markovian, which is a Poisson process. Then there is batch. There is a bunch of other like Erlang distribution and general distribution and stuff like that. Most common will be the Markovian distribution, which is typically on the examples you see MM1Q as the first thing. That's usually the most common and simplest way to study. And then you can try to apply more complex scenarios based on that. So we've talked about how customers enter the queue. The second point is how they leave the queue, like what's the servicing time and what is that distribution look like. Again, if you look at that, it is typically negative exponential service time distribution, where there's a bunch of other types of distribution there. What is most common again is exponential service time, right? That's how most queues would work on. Let's look at the third one, which is, we said it depends on the number of people serving the customers, right? So here again, in a supermarket, if we consider there's a bunch of servers, right now there is a single customers queue where they're arriving into this checkout queue. And this is where they form the waiting line. Instead of having just one checkout counter, they will have two counters now, right? So this is the number of people will be two. So hopefully you can operate twice as fast and customers can enter any queue which is free, right? So this is as simple as counting the number of servers essentially, or counting the number of processes or jobs. Counting the number of processes that are actually serving the request essentially. Next is what is the order in which customers are served. Right? Typically, we've seen first in, first out, which is the classic queue where the first one to enter is the first one to be served. There is other forms like stack. Then there is resource sharing. Typically, imagine, again, I'll try to give some software related example. Let's say in this case would be, imagine you have a process that wants to download a bunch of data, right? And the operating system is going to run multiple processes. All of them are going to share the network of sorts, right? So it's a resource sharing kind of model. Ultimately, internally, it could also be time sharing in some way or a particular resource sharing model. Similarly, you could also have priority queues. In case of, for example, supermarkets, you would have, customers with only small items. They can go via express checkout, for example, or you could have people who need some assistance, so they may be given priority over other customers so that they don't have to join the queue, for example, right? In real world, we have seen all like various kinds of jobs in our software world also that may be priority jobs. The priority jobs can be of two types. One is the non-preemptive and preemptive. Non-preemptive means once the job is started, you cannot like remove it from the process, right? Typically, in case of again supermarket, if you think about it, if I'm already being served at the time, even the cashier wouldn't want to put my order on the hold and then get someone else, right? Typically, usually it is in a non-preemptive way, preemptive way. Sometimes they might also actually do, hang on a second, let me serve this other customer, which is a more priority, stuff like that, right? So this is what we mean by preemptiveness and non-preemptive jobs. There might be shortest job first, like express checkout is kind of one example where if you're just carrying one item or less than 5 items, you can quickly walk through and get checked out very fast. In that also, you could have preemptive and non-preemptive options, or you could also have the shortest remaining processing time, right? So if you think about it, this goes into some sort of a way of how you want to prioritize the jobs overall, right, that are coming in. The fifth parameter is the queue size itself. Like, can you have an unbounded queue or a bounded queue? Right? Is the typically, let's say, queue in the supermarket may be finite because there is no finite number of humans. But again, from a modeling point of view, you might want to consider it to be infinite in a sense that people will just wait for their turn and we don't have to have them physically waiting. Right? Again, purely from a modeling point of view. In case of, let's say, supermarket, it makes sense to make it finite, but in case of software or a bunch of other domains, it may be better to model things as infinite. Similarly, same source of customers where the people are coming from, that also can be finite or infinite in that way. So we've looked at good amount of things around what the queue characteristics look like. These are very high level, like 6 characteristics of the queue. I'll just take a pause here and take a look at if you have any questions before proceeding.
Yes, so I have one question on the previous slide where the source of the queue, right, it being finite or infinite, has a bearing on the system. Is it because it helps you predict that the inflow will stop at a certain time in the future? Or is there something else where the source of the queue being bounded or unbounded has an impact?
Yeah, in somewhat way, that's the case, and purely again from a mathematical like study point of view, having a limit, then the formulae for queuing theory, the theory part of it, right? They can be bounded summations and stuff like that. Otherwise, it becomes
Okay, got
something
it.
tends towards infinity, and then you do
Understood.
a sum over large range, etc.
Got it. But actually, from a software standpoint, I think it's gonna be an unbounded largely, right? I mean,
Yeah, typically, yeah,
it could be bounded as well, but largely unbounded is the use case that you designed for, right? So,
correct. That's correct.
thank you.
All right. So what we looked at is the 6 parameters for any queue, essentially. How people arrive at the queue, the input arrival distribution, the departure distribution, how they leave the queue, what are the channels, how many people actually are serving these jobs, the discipline in which these jobs are served, first come, first serve, last come, first serve, stuff like that. The queue size or the queue depth, sometimes we call it, right? Is that finite or infinite? And the calling source. This is known as the Kendall's notation, uh, where any queuing system you can kind of represent this in kind of this form, and you then have mathematical equations that let you model the queue behavior in some ways. So I wanted to make this a bit more light talk as well, so we kind of have some sort of a break or a joke uh, about queues, because we're talking about queues. So do you have any guesses on if I told my friend a joke about infinite queue, what might be the response? They will get to it. Nice one. Okay. Hint is given the time, I'll spare you with the long pause. Yeah, let's be waiting for the punchline. All right, back to some more theory with an example this time. So let's look at this, right? Like imagine a gas pump or a gas station with a single pump for now, again for simplicity. And we are given something like this, that remember the observation part that I talked about, that you observe something for a long period of time and you find the average and stuff like that. Imagine somebody has done that and they have found that the pump can serve 6 customers per hour on an average, right? And cars arrive at this gas station at 10 per hour, which is exponentially distributed. So given these two values, we'll just look at this one example of a queue and what the formula and how the calculation, like what we can do with just this kind of data, right? What all we can calculate. So again, if you look at deriving or writing this in a form of Kendall's notation, it would be a Markovian distribution for input arrival and output departure, where because we have just one pump, we can say this is a constant one, the number of service channels is going to be only one. Hopefully, this will also be first come, first serve basis, that people who enter the gas station first, they'll try to get their service done first, right? And for the simplicity purpose, we can assume that the calling population and even the number of customers allowed in the queue may be infinite, which may not be the case. But again, for simplicity or calculation point of view, let's say if we're doing that. So what queuing theory allows us to do is if we can model it in certain way, right, our system, there are a bunch of sort of queuing formula for these kind of models, right? What we did is we figured out there is this model that exists, and then if you look at the textbooks and the reference books and theory, you will find that there is a certain number of formula that you can use for calculating a few things, right? So I'll spare you with the details here, but let's look at what all we can calculate. So typically we can say that, okay, the mean arrival rate is here 10 cars for 60 minutes, right? That's what we're saying. This is denoted by this lambda character, where we're saying we're going to get 10 cars every hour. So we can say on an average we get 1 car every 6 minutes, right? Similarly, this mu, which is mean service rate per busy server, means the pump is able to serve 6 cars in 60 minutes. That means it can serve 1 car every 10 minutes. So the utilization factor of the pump is going to be this formula, which will give us the value as 0.6, which is 60%, right? So with just this data, we can say that, okay, the pump will be utilized for 60% of the time, right? What are other things that we can calculate? So there is this formula for WS, which is called expected waiting time per customer in the system. Remember, again, the definition of system would be they enter the supermarket queue, where they enter they get into the checkout queue, right? Like that's the kind of, they are in the system, right? So again, there is a formula where you can calculate and you find the value to be 15 minutes, like 0.25 hours is 15 minutes. Similarly, you can use another formula for calculating the waiting time per customer in the queue. Again, all of these are sort of average values over long periods of time, right? Similarly, you have another formula for expected number of customers in the system. Like if I look at the pump at any point in time, how many cars would I see in the system? Or how many cars would I see waiting in the queue, right? Typically. So again, all of these, if we're able to model the system in a certain way, these are various things that you can calculate. There is also a bunch of probabilistic answers. For example, if you were to say, what is the probability to have 2 cars queued up at any point in time, right? Like you can, there are formulas for some of those based on the type of queue. So we've talked about MM1, first come first serve, and infinite. For different types of queues, there's different formula, and you can calculate some of these values, right? So this gets into the whole calculation of utilization of a particular server. Again, if you remember that slide where there was a graph, the idea is to find out what is the sweet equilibrium point where we can have shorter waiting time for the customers, as well as not increase our cost too much. And that's the whole goal of studying all of this, essentially. Similarly, that's like, I'll leave it at that. I'll give you another kind of problem to think about. Let's say on an average, a server receives 100 requests per second. The average number of requests in the system is 10 per second. Again, this is measured over some period of time. What if we ask, okay, what's the processing time for the request? Right, so 100 requests per second are incoming. The average number of requests in the system is 10 per second. What is the usual, like, what could we guess about the processing time, right? So if you have some sort of scenario like that, there's a thing called Little's law, which says there's a relationship between these 3 components of these 3 parameters, in a sense that the number of requests in line because this line, that's why it's denoted as L, is equal to the arrival rate of the jobs or the queue or the request or whatever the thing happens to be, multiplied by the waiting time for each job, essentially. So this is known as, again, Little's law. So imagine, again, we're able to break our problem down into this manner. We're able to figure out and observe these values, assuming all other things are constants, etc. We can calculate here lambda is 100 requests per second and L is 10 requests per second in this case. So we can reverse the formula in this way and say that, well, we can say the average kind of latency for the API would be 100 milliseconds. Right? So we looked at some sort of a utilization law and what that is with respect to lambda over the mu, and we looked at Little's law. There is a bunch of other laws here with respect to scalability or queuing systems. You have Handel's law, which talks about how much parallelization can you do and how parallelizable is the problem space, essentially, right? Can you just throw more hardware and scale it completely horizontally in the sense by just adding more servers, or is there some sequential component? There is universal scalability law, which is kind of an extension of Handel's law, which talks about having coordination challenges, services coordinating amongst each other, or jobs or processes having to coordinate across other processes. How does that add complexity and why we don't get a linear scale up, right? Like if one server is able to serve 100 requests per second, if you just add one more server, it may not be able to serve 200 requests per second, just like that, right? So why does that happen, and how you can study that more quantitatively? There's a bunch of other like things which we'll skip for now. What I want to talk about now, given enough sort of theory, is okay. How was this used, or did you actually use any of this in some way, or what's the purpose of learning all of this, right? So I want to talk about like two production use cases. Let's start with the first one, where we had an eKYC SaaS APIs. KYC is knowing your customer. So imagine we had machine learning models which would run to do a face match between two images and some sort of optical character recognition for your ID cards and whatnot. And we packaged all of these models in the form of SaaS APIs. Right? We sold this to like B2B customers, and this needed to scale to 2 million machine learning model API calls per day. And that was the scale that was expected. So that is the overall business context. There were some need or the requirement in terms of what the system should be able to do and what we should design it for. So it is, yeah, we need to have 2 nines at least of availability in terms of SLA. We need to optimize the cost because we can't, GPUs are costly. Models require to be run on GPUs. They're super costly. We need to figure out how do we optimize the cost. Also, we need to not have a very large latency in terms of response time, so that otherwise users get bored and the whole work that you did for face matching is and other options is all gone for toss. And so these are some sort of hard requirements that we discuss with business, and I'm summarizing it very high level. There's more nuance and more details, but for now, this was the high level system. So the architecture for the system looked something like this, where we had the client SDK. This was a mobile SDK making calls to our backend server, where they would call via whatever network or any load balancer essentially to get to our APIs. And in APIs, you would upload the images and store them in some storage and have some cache and whatnot. Sort of not important. But ultimately, what you would do is we would make a call to run the machine learning model, right, via HTTP API. This would send a job in some sort of queue. We were using RabbitMQ at the time, and there are these background workers, right, uh, which are the GPU workers or machine learning models that are deployed. They pick up the job from the RabbitMQ. They do the work of matching the image or doing whatever it's supposed to do, produce a result. That result gets written back to the RabbitMQ in a different, like a queue, for example, or topic, and then the API layer consumes that and then returns the response back to the user. So from a user point of view, the experience was synchronous, but from internal system point of view, it was governed by this RabbitMQ, which was acting as a middle queue in between. And they would write data to database, and API would read that and whatnot. Right? So this was the overall architecture. How did we use some concepts for, again, the requirements? If we think about availability, cost optimization, and some latency numbers, right? So we had to kind of load test a single GPU to find out how many requests can it serve over a period of time. Right? What's its throughput? Like, what's the maximum number of requests the GPU, the machine learning model can serve? Because typically in our system, what we identified that to be the bottleneck, right? Where GPU's model again typically take more time, database and other cache components, etc., are going to be easier to scale, and they're sort of proven components where there may not be that latency, right? The most latency inducing part is going to be the ML models. So we load tested a single, like a GPU node, to find out its throughput, and we wanted to also ensure that that is utilized to the 100% or as much as possible, right? Why? Because again, these are costly. If you're spinning up a costly resource and not using it, then you might as well, like, you're incurring more cost than you should. We did some sort of failure mode effects analysis. Again, that's a separate kind of topic for individual components and their interaction. What I mean by that is, again, load testing specifically only APIs or just the workers, like the top case that I talked about, but also load testing third parties or the components that we're using, RabbitMQ, Benio, Postgres, Redis, etc. Right, and also interaction between these components, because that's when the whole systems come together and it actually works, right? So obviously you do some sort of unit level testing for these components, and then there is component end-to-end kind of testing in some ways, right? What we also realized the hard way, I'll cover that later, is why a good amount of end-to-end observability for each of the handoffs of at each of the queues is needed. What I mean by that is, you can think of the whole thing as one queue where customers sending the HTTP request and ultimately after some time getting served. So that's the overall latency. But you can also break down that same component to multiple sub queues or sub components, and you can think of it as queues at multiple levels. Right? For example, the request has got to this API, and then it is being sent to RabbitMQ. So what's the time it takes for that to happen? What is the time it takes for the worker to be able to pick up that task? Stuff like that, right? In some way, you could say that we were looking for some sort of a trace, essentially. Like, what's the overall trace for a request and where the time is being spent? We did not have it at the start, right? So this, we realized the hard way that why this is needed. And again, we wanted to, or we had to build some sort of a custom autoscaler for just scaling these ML workloads, because those are the costly resource. So you want to ensure that you have enough capacity, but at the same time not have too much to be able to incur more costs, right? So there's a lot of tuning and lot of number crunching, lot of, I wouldn't say modeling as such, but a lot of data around individual components and their maximum scale we had to do. So there are two issues that I want to talk about that we ran into, and then we had to we had to make our way around that. So we were using Nomad at the time as a orchestrator for running these workloads. And this issue, as I checked literally, I think yesterday, this is still open, where allowing Nomad to run or share a single GPU across all jobs, right? That is still not possible. We did that in a workaround way using uh, raw exec driver of Nomad, which is what my comment talks about. But this is one. So just to quickly illustrate that issue, the idea was that imagine this to be like a GPU where as Nomad you are launching Docker containers onto the GPU and you're saying, hey, run this container on this GPU node, right? You cannot kind of run more than one instance of the container on the same GPU, even though the GPU memory and the GPU cores and the cache and the other resources on the GPU are available to run this, right? So we kind of solved it by using the raw exec driver where we bypass Docker and where we are able to run multiple workers. Uh, we were able to actually fit 4 Docker containers on a single GPU, the Tesla T4 GPU that we were using at that time. That brought down our cost straight by 4x, and not by, I mean, like 4%. It's like four multiple of 4, right? So you would have to otherwise spend $100. We ended up spending only $25. That was a massive saving. Uh, Second sort of production issue that we got into, which is again kind of touches a bit on some of the concepts of queuing, is we started seeing more than 25-second response time after certain scale. So we rolled this out on production to all the users or more number of users, and then we see that there is more than 25-second response time, and we are breaching our SLA. Like, what do we do? Where is the problem, right? And at this time, we did not have a really good tracing enabled on production, and we were still setting this up as we went along. The first culprit that we thought was, hey, there has to be like problem at the worker, right? Because those are the those are the smaller, that's the component that is latency inducing. Because so there may be more jobs queued at RabbitMQ because of which the workers are not scaling up or whatever. But we looked at the RabbitMQ metrics and there is no queue depth, as in the queue is not piling up there. So where is the problem? We're like, okay, maybe it is at the worker something. So we're trying to debug and figure out individual worker, how much time it takes, and we're like figuring out stuff on each of the workers by manually logging in and whatnot. But again, for the most part, we couldn't see massive processing lag as such. Like that would indicate why is there a 25-second response time, right? From a user point of view. And we just couldn't figure that out for a good amount of time. This incident led to a couple of hours. Ultimately, what we realized is that, the system design that I talked about, where the workers, when they complete the job, they write it back to the RabbitMQ, and there is a go routine in the API layer which reads this data and then sends the response back to the user, right? Of sort. Again, simplifying the case overall. So this number of go routines is just 5. And because we knew that the API pods were not that, like the CPU utilization, memory utilization on those pods was way below the 100% value. There was no need to scale these. And there was just only 5 go routines. This happened to be like a configuration that we used on staging for testing. So that just happened to get pushed somehow. And after realizing we changed this number of go routines to 30, suddenly the latency dropped and things started becoming normal. So what I want to kind of highlight is when you have problem at one level, like where the back pressure kind of gets to the system and where some throttling happens, it becomes very difficult to have a end-to-end view unless you have a good observability of almost like a trace of every packet and you see where things go wrong or take more time. Right? So some sort of things that we had to use almost like Amdahl's law in terms of can we just add more workers to make this more parallel, and how many workers should we add if we wanted to support 2x of the traffic, right? So for that, we kind of had to do some back of the paper napkin kind of math for using Amdahl's law, some bit using the scalability law. Again, these are all, there's actual formulae for all of these laws, or some of them at least, but our analysis or our use was more quantitative and more experimental by actually checking a few things, and knowing these laws or knowing these concepts helped in figuring out some numbers that we can trust and we can model with, right? That's the purpose of this. And I take a pause, and we'll talk about the next issue. At the same time, I'll wait for you to, if there's any questions, I'll help answer those.
Yeah, there's a few questions in the Q&A section, Chinmay. I can read them out if you want.
Okay, can you give me example of ordering customers? Yeah, I think stack, although it is there in the queuing system, I couldn't think of a good practical use case where we use stack. So not really sure about uh, where a stack kind of model would be used for queuing systems. A question by Sagar is, what does the end-to-end observability look like for the setup? If you're talking about this case that I described, ideally we would like to capture metrics at every level. Essentially, what we want to be able to track in case of any data pipeline, or in case of any like end-to-end queue, right, is metrics at each component level, straight from request coming to the server, what's the time there, and as that request passes through internal services or components, what is the time at each interval. In some cases, if it is asynchronous, it's difficult to have uh, sorry, Sagar, you want to.
Yes, so basically I wanted to know what was kind of the technologies that you use for having the entire like the trace of the request from start to the workers and all those things, because I've seen OpenTelemetry being a good case for that.
Yeah. So this was a bit before OpenTelemetry was a good sort of standard as such. We still didn't end up implementing full traces. We hacked some small way to get metrics typically for workers, and this handoff between API and the worker, because that's where we realized the production issue that I talked about. So ultimately, it was still not the strongest observability setup overall, but we captured infrastructure and service metrics mainly. Logs were decent, but the whole tracing was still not there on production, and that turned out to be fine still. It's just that we had to pay the price by due to that issue. But otherwise, we once we fixed that, there was not similar issues that would require more tracing. If that answers the question. Rohit Dev is saying, what toolset are you using for measuring rates across components and overall stack? Trying to understand context for this.
And basically, what kind of APM tools are you using? Are you using any commercial tools, or like you guys have built something?
Yeah, so back then again, we hacked together a few things in certain way. For metrics logs, we were using Prometheus, and I believe it was Paper Trail just for logs, not a very fancy thing. And there was also no centralized observability solution as such. But if I were to do it today, I would probably use some like centralized observability solution if the budget of if there is enough budget for these kind of things. Yeah, the next question is after the incident, did you consider having a dynamic number of coroutines in the API? Yeah, we made this a point also in the API that almost like a very ugly check. This was done to say that if the number of coroutines is less than a particular value, API should not start. Like we should at the minimum spin up X number of coroutines, and that X we made it configurable in that way. So this gave us some confidence that this kind of issue will not happen again, where a developer accidentally, whatever reason, somehow pushes the local config or staging config to production. Right? It wouldn't happen. So that was the idea. Okay, going back to the break. Yeah. So what's the worst thing than having to wait in the line? It's like having to wait in the wrong line. Like that's clearly worse, right? Okay. Cool. Let me move to the next case study, and I'm also checking the time. So this one again is a sort of specific. What we had was, imagine a vulnerability scanning SaaS tool, right? Like where I can, like we are offering this vulnerability scanning APIs to the B2B customers, where the scale can be all my infrastructure assets. It could be in tens of thousands or whatever. So imagine like 10,000 assets or targets as they're called. And there is some templates using which I wanted to scan them. I want to check if a particular port is open, or what's the TLS version, or the DNS record, or specific things, right? So imagine you created templates for these, and I want to run end-to-end kind of combination. Right? So just for a single B2B customer, if you multiply these two together, because they would typically be, every target would, worst case, would run all the 6,000 templates, right? It would amount to 60 million runs. A run here, I would mean one target and one template combination, right? These are some things that this would be the scale at which we would have to design the system. And this, typically these scans are repeated at a specific interval. It could be a day or a week or something like that, right? So you would want to make sure that you get notified of any open ports or any open vulnerabilities before attackers discover it. So you almost do these routine checks every now and then, almost scheduled checks, right? So that was the scale that we were dealing with. Again, in terms of very high level requirements, I'll say availability, cost optimizations, and in this case, there was not much latency requirements, because these are, by definition, these are kind of batch jobs that will take some time and run for a long period of time, and nobody's expecting the results to be in immediately. If you look at the previous eKYC case, that case was still synchronous, in the sense that from a user point of view, I'm waiting for the result, right? Even though internally we had asynchronous modeling for the system, but as a user, I'm still waiting for the results. Here it is purely synchronous, in the sense that user can actually check the progress and check how many scans, etc., are completed, but they don't care about latency as such, as long as these scans eventually get completed, right? So that was the focus was then more on how do we minimize the cost for running this infrastructure and ensure the utilization and the throughput overall is more, right? Because we're dealing with a large scale. So that was the kind of dynamic of the environment. Again, if you look at the architecture, it was sort of similar to what we had before for the eKYC, where you would have user, load balancer, there's some API. In this case, we were using Kafka, so you would send the job, if I may call it that, to Kafka, and then there are these workers. These are not now machine learning workers. These are just sort of pure CPU workers, where they would take up a template or a job or whatever combination, and they would do the work of running that job and update the status in DB, and API would get that and whatnot, right? It's pretty standard stuff. So what was the challenge here, right? So imagine, like, I, as a customer one, come in and do a large scan. Like large scan meaning I have like 25,000 targets, and I'm running them across 6,000 templates. So 25 into 6, 150. So it's like 150 million runs, if I were to call that run, right, as a terminology, would get scheduled on my infrastructure. While this is happening, after some time, while this thing is scheduled, after some time, a small scan comes from a different customer, right? Which takes like, okay, maybe 10 targets or 100 targets or whatever, right? Very small scan compared to this large one. What would happen is typically the things they would get scheduled would be a large scan would be scheduled first, the entire large scan, and then the small scan will be scheduled at the back. So it's almost like a head of line blocking, right? Like it's like in the supermarket, you are standing behind someone who have like 2 truckload of carts, right? And they are like literally ordering like thousands of dollars of goods in supermarket. And if you stand behind them, it's going to take you forever to get served, right? So that was the kind of problem that we saw because of the way things were architected before. Now, what are the like very high level sort of challenges with this kind of thing, right? Like one was, as I said, a large scan from one tenant, one customer can slow down other small scans from other tenants. Like they'll just be waiting, right? Even though they can be served within very short time, but they just like be standing behind a kind of large scan, right? To be waiting to be served. The whole capacity planning for the hardware and the scaling of the workers could also was also challenging in the sense that imagine somebody runs a large scan and we spin up a huge infrastructure and that scan gets completed. And there is nothing behind that scan. Like there is just a small number of scans after that, right? We would have to have very spiky workloads in a sense, and we would have to write autoscaler that does very drastic things in a sense that it shuts on all 25 machines or all 100 machines all at once. Or if we do it gradually, then we are actually still incurring a lot of cost, but all of these machines are not being used anyway. So the whole designing of this autoscaler and the orchestrator was becoming very challenging. Because of that, the managing of infrastructure costs was challenged. Ensuring high throughput and the worker utilization to again make sure that the capacity is just enough was a challenge, right? So this was a very high level problem. How we solved it in some way is that we said, look, what we do is imagine there is these large scan, small scan, medium scan. This is the order that they come in. We, instead of having a single topic in Kafka, what we would do is we would have sort of 3 topics, almost like think of it as a highway lanes, right? Like you have a large lane only for trucks and heavy vehicles. They should all go, any large scan, they should just go there. Any small scans can go into small queue or a separate topic, and any medium scan could go into this medium. So we almost like bucket our scans because we know this upfront. When users schedule the scan, we know that they're running this for 25,000 multiplied by 6,000 or 10 multiplied by 20, right? We kind of know that already. So we bucket them into these separate lanes of sorts. And then we could also have separate workers, node pools, where we could have small workers will only pick up small tasks. Again, this is almost like a express checkout lane in supermarket or a priority lane, a priority boarding at an airport. Think of it like that, right? So the concept is this highway lane where imagine you have a separate lane dedicated for trucks or heavy vehicles. Then one vehicle getting behind another shouldn't be a problem because you can design policies for scaling in terms of workers much more easily. And you can almost like you've broken down the problem at one level into 3 sub problems, right? Which are similar in nature. So that made it easier for us to deal with this. It isn't like a perfect or a 100% foolproof solution. There will still be head of line blocking in some way, but one truck will block another truck. One truck won't block a Ferrari or a fast moving bike, for example, right? At least we kind of made ensure that. And then from a business point of view, that requirement was good enough. So I'll move on quickly. There's a bunch of things that I did not cover about Amdahl's law, like the actual law with details, the scalability law, the service demand, and equations around that, and how it works and what these are and what to make sense of them. We touched upon some bit on throttling, back pressure, etc., but not too much. There's also something super interesting that I learned from one of the colleagues. It's called Rasmussen model, which is a trade-off between performance, cost, and capacity. Like super interesting read. And we didn't talk about queuing behavior where users don't even want to get into the queue if the queue is too long, right? We all do that in real life, or we jump lanes, jump queues, right? Things like that. But yeah, that's probably for some other time. If you're interested in this kind of stuff, then these are some books that I read, or I kind of still keep going through them every now and then. Performance by design, I think, is super useful, and some of them are very technical, very mathematics oriented, especially this introduction to queuing theory. But good to kind of get your feet wet if you're interested. Lastly, yeah, I write on Twitter on some stories about this kind of work. I've also developed a Go Bootcamp. We have a playbook for a company where we talk about how we do things at 1 to N. If you are interested, yeah, do check us out. If there's any questions, I'll take those. Yes,
I
please.
think Mayank has a question. Yeah.
Yeah, go on.
Yeah, Chinmay, in the last example that you took, how do you prevent resource starvation and long waiting times, given that you've already batched it? You solved the head of the queue problem, but typically the larger jobs will always get lower priority to increase throughput, right? So small batches over large batches, right? So did you introduce some kind of time related priority where if a job is waiting in a queue for an X period of time, would bump it up in the processing queue or something like that? Because otherwise you would still end up with the same challenge of low utilization, right?
Correct. Yeah, so I think we haven't encountered that yet, that problem. But what the kind of things that you described, maybe those are some solutions. Like one way we have mitigated this, and from a practical point of view, this is good enough mitigation, which is just separate the 3 types of job. Like you might ask, why 3, why not 5, why not 7, why not 2? So in that case,
Standard bucketing model, I get that.
correct,
But
yeah.
what I'm curious about is the larger jobs, right? Because ultimately you are sort of creating broadly 3 priority queues in some
Correct.
sense, right?
Totally.
Based on size. So given that you don't want one large job choking the entire system, you would typically prioritize the smaller queues, which means there is a chance of starvation. So I'm curious about, did you apply any mathematical models for that, or this was just good enough and you guys never saw a problem after this?
Correct. I think this was still good enough in a sense that this wasn't a problem in this case, because what we also did is that we separated the workers for these jobs.
Got it.
So a small worker would never take up a large job, even if large workers are overloaded. So we almost said, it's almost like this. This also helped us in a sense that we said that any new customers, any new signups, we will have some limits on them, what kind of jobs they run, right? So any free customers can be served by these small workers, which could be on preemptible nodes and whatnot, right? Stuff like that. So that way we can also do, kind of did not get it to that scale yet where we have to worry about this
So
problem.
you introduced back pressure implicitly, and you're doing that load balancing implicitly, but in this case, it is an explicit boundary. Understood.
Yeah.
I was considering a situation where all of these workers can, if they are free,
Okay.
for example, pick up one of the larger jobs, right?
Correct.
In case there is an extended waiting time. Because even so typically your larger workers would be large corporate customers with hundreds of machines, and then if you always delay them, then you have a bigger problem because they have 95% of your revenue, right? So okay, maybe I'll take this question with you offline because I don't want to hijack the talk, but would be interesting to discuss this with you.
Yeah, definitely. I believe Evan also has a question.
My question was more about further learning resources. The books you shared in the last slide do cover the queuing topics, but I believe they are more from a technical or from a theoretical standpoint, or more mathematical. Are there any blogs, conference talks, or books which cover this topic in a more approachable or more from a developer standpoint?
Yeah, interesting one. Uh, I don't have a list of these sort of handy. Some things that where I got interested in them and I've learned a few things is like following Neil Gunter, if you know, like his work when he's the person who came up with the universal scalability law. So some of his books, I think this is his book, the Guerrilla Capacity Planning, and overall his blog or his Twitter, etc., has been useful. He was at one of the conferences where I met him and discussed a few things. So it's kind of random. I don't think I have a nice list of more approachable things. Yeah, I'll try to collect that maybe sometime in the future, and yeah, and see if I can help out on that.
Thanks.
Here is a quick new question. In case of RabbitMQ, from example one, didn't you face bottleneck there? Was there any partition as configured? Yeah, so we did not have any problems with the queue itself because again, 2 million requests, it wasn't the case that they would all come at the same time. And we had load tested RabbitMQ by sending like 4x or even 5x of what load we would expect. Right? So we had tested it to send like 5x of the peak load that we would expect. And we didn't face any problems. Like we were using queue mirroring, and it was still a self-hosted RabbitMQ with good IOPS, disk IOPS, and stuff like that. But apart from that, there wasn't a bottleneck at the RabbitMQ side. It's that the bottleneck wasn't there at all. We were just kind of it's almost like if you drive your car in a load mode, typically automated cars, right, or in the second gear, for example, and you try to go beyond 50 or 40 or 50, right? Like there would be so much noise that the engine would generate, and if you just drive it in a sports mode or in a fourth or fifth gear, it would just go smoothly. That literally was one of the bugs that we encountered, and that was very stupid, or it was almost self-induced in that way. But all the components that we use, Rabbit, even Minayo, for loading images and at scale wasn't a huge problem.
All right. Any other questions at this point?
Oh yeah, sorry, I don't remember the machine configuration. Sorry about that, but like you can do some sort of load testing to come up with some number. Not very crazy, like 16 CPUs and like 32 gigs RAM. Nothing of that sort. Very standard, maybe 4 CPU or 4 vCPU and like 8 gigs of RAM. That kind of one machine, if I remember correctly.
All right. I think there are any other questions, I'm sure you can shoot them
Yeah.
at his Twitter handle. Or
Yeah, do reach out. Hopefully this was useful for people to get a gist of how do we, not just learn about theory, but understand how it practically fits and how it was useful. And that's why I wanted to cover more like production use cases or things that we actually did, and then just pure theory. Hopefully that was useful.
Awesome. Thank you so much, Chinmay, for taking the time and talking about this interesting topic. Thanks everyone for attending.
All right, thanks.
Thanks. Bye bye.